first talk for this session is in database learning with Sparse Tensor, and Maximilian is going to give the talk.
Okay, welcome. Yeah, so my name is Max, and this is joint work between my group in Oxford, Relational AI, and also Long, he's at Michigan and part-time Relational AI. And so what we are trying to do at a very high level is we exploit algebraic structure in the data to lower the complexity and improve the performance of computing optimization problems over database queries. And when I say algebraic structure, what we really mean is like a database schema, join dependencies, and functional dependencies. So that's a high-level overview. And in this paper, we provide a unified problem formulation for a host of optimization problems like regression, factorization machines. And then we give an in-database solution to this problem and we consider continuous and categorical variables. Also, we provide runtime guarantees, which are best known to date, and they should be very familiar to many of you here in the audience. And we have prototyped and benchmarked our system as well, and for that I will refer you on to our Deem talk on Friday. So if you want to hear more about that, do join us on Friday as well. And now I want to start with like another high-level overview, but for what is done in practice typically to date, right? So I told you we usually have some kind of database query, and we want to compute a problem on top of it. And in our scenario, we call this database query a feature extraction query, because this query, the output, provides us the features which we use to learn a model. And then we have a database, and in practice, we materialize the output, export it from the database, import it into some machine learning tool like R, TensorFlow, what you name it, and then you learn the parameters of the model that you want to learn, right? And in case there are categorical variables, you would need to one-hot encode them, and I will tell you what this means, right? So we don't do any of these three steps I just told you about. We want to completely avoid them, and instead we do a bit of a rewriting of the model. So we have a model reformulation into our unified problem formulation. We rewrite the query into aggregate join queries, and then we compute them in a factorized way. It's a very efficient way to compute aggregate join queries, and then use the model reformulation and the aggregates in gradient descent to learn the same models that you would have gotten, the same parameter that you would have gotten through the typical approach, right? So the green part is what we do, and I will tell you more about this here. So, and now let's be a bit more specific and consider a typical retail example. Here we have an input database D with three relations. So we have sales, stores, and items, which give us the number of units sold for a given item in a given store, the city where a store is located in, and as well the price a consumer would pay for a given item, right? And our feature extraction query here is simply the natural join of these three relations. And then we want to build a model which predicts the number of units sold based on all other variables, and I denote this by this set F. And parameter theta, and our task really becomes learning the parameter theta. Right? So next, I would like to tell you about our unified problem formulation before I tell you how we then compute this problem. Right? And I need a bit of notation to do so. So each tuple in our query result is a training sample to train our model. Y is a value for the label, which is the number of units in our example. X is a vector of values for the variables in the set F, so all other variables. And X subscript V is X restricted to the variables in set V. Okay, very simple, just so you can follow the formulation. And then in a query, or the variables in a query can have two different types, right? We have continuous or quantitative variables, which is, for example, price or number of units sold. We can aggregate over them. And categorical qualitative variables, like the city, item, and in our example, we also have store. And in practice, in machine learning, if you have categorical variables, you need to one-hot encode them. And what does this mean? Let me remove that. So I will introduce it by an example. Let's assume that our input database has can take three values for city. So we can have Houston, Austin, or Dallas. That's a domain for city. And then if you have a tuple which takes the value Houston for city, we would encode it as an indicator vector. So this is this one-hot encoding, right? In the sense that we get this vector 1, 0, 0. If you can imagine that if you have a lot of categorical variables, which in practice you will have, and you always one-hot encode them, and think about, like, I don't know, the number of cities you have in the US or something like that, then your input data set for the optimization problem becomes very large, and you have a lot of zero values. And in fact, when machine learning people talk about sparse data, it really comes from this one-hot encoding. That's one of the big reasons why they have sparse data. So obviously, we don't want to do that either. And what we do instead is we use a sparse encoding of categorical variables. And the way we do that is we encode them as functions, which I denote with H here. These are really feature mapping functions, which map the value for a specific categorical variable to 1. So it's a sparse one-hot encoding. And for uniformity, we encode continuous variables like this. So it's a function which maps the empty tuple to the value of this continuous variable. And then for the sake of completeness, we also consider products of continuous and categorical variables, which in case you have two functions, generalized functions here, then the product becomes another function where we take the union of the variables in the head, and we take the product of the values that the two functions map to. And I want to point out that this set, I hope you can see it down here, the set Vj union Vl is a union of, or is a set of categorical variables that follows from this derivation, and the value we map to here is a monomial of continuous variables. Now, this encoding is what we use to encode our model, our unified model. And I will explain that by the example of linear regression just because it's the easiest to do, but there are more models that we could capture in our unified approach. So what is linear regression? In linear regression, we encode our features exactly like I told you, and we have one of these encodings for each variable in our set F. So we have a price here as a continuous variable, so we map the anti-tuple to the value for price. And then for the categorical variables in our database, we map the value for this categorical variable to 1. And we store all of them in a vector H. So this becomes a feature mapping vector, if you want. And then corresponding to each feature, we also have a parameter. This follows from a linear regression model. And we encode them in a function, parameter mapping function G, which maps a tuple to corresponding parameters. So we have feature mapping functions, which are denoted H, and parameter mapping functions, which are G. And we store the parameter mapping functions in a vector G. And then our unified problem formulation becomes an inner product of the vector G and the vector H. So I don't have time to go into other problems, but like degree 2 models, for example, which are nonlinear, such as polynomial regression or factorization machines, even principal component analysis, they can be encoded in this framework as well. So feel free to ask me questions later or come to the poster and I will tell you more about this. So, but the bottom line is we have a model which is the inner product of G, vector G times vector H. And I also want to point out specifically that the parameters only come up in this vector G here. So now, having a unified problem formulation, how can we actually compute it? And remember, computing for us means we need to learn the parameters in this vector G that best explain the training data. And we do that by minimizing the least squares loss function. So the least squares loss function really takes, for a given tuple, the prediction that our model gives, and it takes the difference to the actual value that the training data gives you, squares it, and then sums up over all the tuples in your training data set. And we also add here a L2 regularization term, which is used to avoid overfitting in the model. It's essentially a penalty term on the parameters, so they don't explode. And then we minimize this by gradient descent optimization. Gradient descent optimization in a very simple case is really straightforward. We update the parameters in the direction of the gradients repeatedly until we reach convergence, right? So bottom line is we need to compute a function j, the least squares loss function, and the gradient of j. So how do we do that? First of all, I want to start with a rewriting of this j function in matrix notation, because it will exemplify what we do a bit easier. And for that, I define a matrix big H that contains all the feature mapping vectors for each tuple in our database, right? Remember, we go from a tuple to a feature mapping vector H, and then big H just contains all of them for all the tuples we have in our database, or in our training data set. And if we define this, we can rewrite this least squares loss function as follows. Now, it looks a bit more complicated than it really is. The important bits here are that we can define three quantities, sigma, c, and s. And once we have defined them, we can compute the gradient using sigma and c. Why do we do this? Well, very straightforwardly. Sigma becomes a matrix of size m. And remember, m is the number of features that we have in our model, or m times m, right? The matrix of size m times m. C is a vector of size m, and S is simply a scalar. And all of them are independent of the parameters. So when we do gradient descent, and we update the parameters continuously, these quantities, sigma and C, don't change. So we can pre-compute them once, and always reuse this pre-computed quantity all the time. This means for us that gradient descent optimization is independent of the size of the training data set, which is great for our complexity results, right? So we do gradient descent optimization without ever touching the original training data set again, and we just learn over these quantities sigma and c. Now, obviously, the next question is, how do we compute sigma and c? And that is actually, in database terms, very easy to do, because, and let's consider one index in the sigma matrix. So we consider sigma JL, and this is a group by aggregate, standard group by aggregate, defined by a function here, which is the product of the index J and the index L in our feature mapping function. So we get this function here, and the group by aggregate then uses the definition of this function, and we get this SQL group by statement where we group by a set of categorical variables. So categorical variables translate into group by variables. The monomial of continuous variables becomes a sum aggregate, and we compute this query over the result of our feature extraction query. C and SY are computed also as group by variables, group by aggregates very similarly. And so bottom line is, all of these quantities are simple group by aggregates that we can compute directly in a database. And that is great. And since we compute group by aggregates here, we can avoid one-hot encoding the input data. Right? Another optimization we do is we exploit functional dependencies. And we do that to reduce the dimensionality of the problem. I'm not going into many details here because it can get quite tedious, but at a very high level, consider a functional dependency store determines city, right? So if we know like the store, we know which city the store is located in. And we can extract a map, R, just call it R, for which the feature mapping function for city is equal to R times the feature mapping function for store. So we exploit this functional dependency here. And then we can replace H city by this quantity R times H store. And the result is that we compute less aggregates overall, which is great for us. And then we rewrite the regularizer to optimize out all the parameters which correspond to city. So we also compute less parameters, which is also great. And what this really results in is a reparameterization of the model, which excludes the parameters that correspond to city. Now, what I'm hiding here, and I don't really show, is the fact that the regularizer becomes a little bit more complex than it was previously. So we take away a bit of the computation from the pre-computation step of computing the aggregates, and we add a little bit of extra computation to the gradient optimization step. But in practice, when we implemented this optimization and exploiting functional dependencies actually helped a lot. So it's still a great way, great optimization. And then the next step is we learn the reparameterized model. And finally, at the end, we can recover the original model and the original parameters from the learned reparameterized model by using the map R that we extracted before. And last but not least, we factorized the join computation, or the computation of the join and the aggregates to achieve the best known complexity. And I really don't have time to go into the details of that, but I do encourage you to check out our previous work on factorized databases and FAQ queries. And we also at least try to have a high-level overview on our website. So if you're just looking for some intuition behind it, do check out our website as well. So this brings us to the complexities. Like what is the complexity of our model? And here it is. It looks a bit complicated, but really what is important here are the quantities that are highlighted in red. So let's go through it step by step. In general, or the general formula we provide in the paper, which holds for polynomial regression and factorization machines or all other models that we consider, the governing quantity is the size of the database to the power of FAQ width of the query. For linear regression, we can be a bit more precise in the sense that the governing quantity is the size of the database to the fractional hypertree width plus 1. And to put this into context, if we just compute the listing representation of the query result, then this is governed by the size of the database plus to the power of rho star, which is the fractional edge cover number of Q. Now, if you have never heard of any of these quantities, don't worry. All you really need to know is that there is a gap between rho star and the FAQ width, which can be up to the number of relations in your query. So this means that in asymptotic complexity, we can have an exponential gap between simply computing the result of the query and our end-to-end solution to compute an optimization problem. Notice that if you just compute the result of the query, you don't even compute anything on top of it yet, right? That's extra. So we don't solve an optimization problem. So in terms of complexity, we get a great result here. And at the end, I just want to show this because we did implement it and we did benchmark our system a lot. We compared against TensorFlow and MATLib and also LibFM on a real data set. And as you can see, the speed up, we can have orders of magnitude speed up in practice as well. Also, this data set here on the right exploited a functional dependency, which gave us an additional speed up of 3.9 times for factorization machines. And now I'm happy to take questions. Of course.
So, sparseness is a way that we can take advantage of sparseness. So if I have a metric which is, let's say, 1,000 by 1,000, it would be expensive unless I take advantage of sparseness.
Is the mic on?
Is the mic on?
Yeah.
Yeah.
Doesn't work.
So if I have a matrix 1,000 by 1,000 or maybe million by million,
It's supposed to be for the camera.
Is it on?
Just take it.
That is a charm. If I have a large matrix, million by million, I won't be able to do it unless it was sparse. But you seem to be generating sparseness by blowing up the size. At that, I'm mystified by why would you benefit by blowing up the size. For example, I can represent a Boolean function by a circuit or by a truth table. Mm-hmm. And you essentially use a truth table representation. What's the rationale behind it?
I don't think we really...
Yeah. One hot, first of all, is this is how you create sparseness. One hot.
Yeah, but that's exactly my point, right?
But you create, by you representing by this array, essentially, this array, think about it, if you have a Boolean function,
yes.
You represent the truth table, which is a function from the value of all the attributes to the truth values.
I fully agree with you.
Yeah.
That's why in our version of this solution, we don't one-hot encode. Right? One-hot encoding is done typically, and I'm sorry if that wasn't clear enough, it's typically done in practice, but not for us. I mean, we avoid it by using this functional encoding, this sparse encoding, right? And then what we really do is compute group by aggregates, which, not sure if I get there, right? So this one-hot encoding is only done is typically done in practice, but we don't do it. We encode it in this functional form, in the sparse representation. We still need a one-hot encoding in order to be able to learn the model, but we use a sparse representation of it to avoid exactly the blow-up that you would usually get in case.
I'm still mystified, but...
I'm happy to take you through it at the poster or after the session.
So what are the limitations of what we're doing when you can apply your techniques? What are the types of models you can learn, and why is that, and can you extend it to other types of models?
So what we do here works very well if the model is in some kind of sum product, can be expressed in a sum product semi-ring, essentially. This is when we can rewrite the model and compute the matrix sigma and factor out essentially these aggregates. There are a lot of models out there where it doesn't work so well. So you cannot factorize out this computation, but that's just something we have to deal with. An example for would be logistic regression, because the logistic function, you need to take an exponent, and then it's no longer expressible in a sum product semi-ring, for example. So there are certainly some limitations, and we are aware of that. But in case you can express it in a sum product semi-ring, then this is definitely, we would argue, a good way to go.